Hi, I'm Chris, and in this video we're going to be taking a look at a related rates problem. A few of my students this week have actually asked about some specific problems from a calculus text that they're working out of, and so I wanted to cover a few of those. Most of you in a lot of your textbooks have answers to the odd questions in the back of the book. If you happen to be using this text, it's the Larson calculus text, then you have answers to the odd questions in the back of the book, but you also have a great website. I'll post the link on this video. It's called calcchat.com, and it has not only the answers to the odd numbered questions, but it also shows you the step-by-step explanation of each and how to solve. So if you're ever stuck on an odd number question, or you're looking in the back of the book and you're not too sure where that answer choice came from, that's a great resource that you have available to you. Today, if you notice, we're going to be taking a look at question 26, which is from page 155. From this textbook, and it's an even number question, so you don't have the answer to it or the explanation available through CalcChat. So I'm going to go ahead and post that explanation, step-by-step way of solving this here. So for related rates, the most important thing is to make sure that we can identify what the equation is that we need to use for a particular problem. These are the kinds of questions oftentimes that deal with a lot of geometric equations involving volume, surface area, Pythagorean theorem, and a few other more complex, like volume and area kinds of shapes, spheres, cones, etc. So in this example, introductory example here, we're dealing with a triangle. So hopefully you've already been introduced to related rates as a general idea, and most importantly, you need to know how to do implicit differentiation in order to answer a question like this. So if you're not familiar with how to work with related rates and you need a more introductory lesson, then please feel free to take a look at the links shown here for maybe one of our other videos that covers something a little more basic. And if you're just getting introduced to implicit differentiation, then you definitely want to take a few steps back, make sure you watch a few of our videos on implicit differentiation, and then build up to a more complex related rates problem like this. All right, so let's jump in. This question, I believe if you read the question in the text word for word, describes a scenario with a construction worker pulling a wooden plank up the side of a building or up a wall, but we've gone ahead and simplified it so far with the information just given in the diagram of the question, which tells us that the plank itself is 5 meters long, and it's being pulled up the wall at a rate of 0.15 meters per second. So I labeled these other sides A and B just so that it looks more like what we're used to seeing with a triangle, which is a right triangle that has sides A, B, and C. And in this case, since we're dealing with a right triangle, what kinds of equations do we know that relate the sides of a right triangle to each other? So hopefully you might have said Pythagorean theorem, and that's absolutely correct. Pythagorean theorem is a squared plus b squared equals c squared. And if you're a high school student in AP Calculus, or if you're a college student taking calculus and working on related rates, Pythagorean theorem is certainly something that we should have mastered by this point. All right, so now what we have to do with any related rates question, a rate is a change in something over time. That's really what rate means, just as a general concept. And that's really what a derivative is. A derivative is a rate. It's change over time. So what you're going to do is take the derivative of this expression, and this is where implicit differentiation comes into play. So using our power rule for derivative, we're going to go ahead and differentiate a squared into 2a, but then we have to multiply by dA dt, which is the change in a over time. And we're going to do the same thing for b and for c as well. This will be plus 2b times dB dt, and that's equal to 2c times dC dt. So now we've got our equation, and there are a few values from this equation that we have already. For example, if we look at our triangle, we know the value of c is 5 meters. So we got that one checked off. We also know the value of dC dt because this plank is not changing in length. It's being pulled up the side of the building, and it's going to change maybe its angle and its positioning, but the actual length is not going to change. So dC dt, we also know a value for. That value is actually going to be 0 that we're going to plug in there. And I'll go ahead and write that. Maybe we'll start listing our values over here. So dC dt is going to be 0. Now for A and for B, we don't have those values just yet, but dA dt we do know. It's increasing at 0.15 meters per second. So I'm going to list that down here as well. dA dt is 0.15. And then for dB dt, for this particular question, that's actually what we're being asked for. So we'll put a big question mark by that one, and that's what we're going to solve for. Now for most related rates questions, as is the case with this one, they're oftentimes going to ask you what's the rate that something is changing at a specific point. And for this question, they want to know the rate when B is equal to 2.5. So when this plank is 2.5 meters away from the wall of the building that we're looking at in this example, that's when they're asking for this particular value of dB dt. So if we match these up, we know that C is 5, as we said before. Actually, let me just move this over here to this side. So we've got C is 5. We've got B. I'm just lining these up with the dC dt with C, dA dt with A, and so forth. So B we know is 2.5 in this example. And then A we don't know yet, but we can figure out, because if we use our original Pythagorean theorem, we could solve for this missing side. Now I'm hoping that some of you might look at this and say to yourselves, oh, you know what? I recognize what type of triangle I'm dealing with here. Anytime I have a leg of a 90-degree right triangle, that's half of the hypotenuse. That means it's a 30, 60, 90 right triangle. If you recognize that, awesome. You're a step ahead of the game. If not, no worries. You can still solve for A by using Pythagorean theorem. But we're going to assume that we can recognize the 30, 60, 90 right triangle, because that's something really important that's going to make a lot of your questions easier if you can start recognizing those special rights. So here, A is going to be 2.5 times root 3. And then now we have everything we need in order to just plug in and solve. 2.5 root 3 for A. And when we go to plug in all of these values, we have 2 times 2.5 root 3 times dA dt, which we said was 0.15, plus 2 times B, which is 2 times 2.5, times dB dt, which is our variable that we're solving for. And then C and dC dt we had from the get-go. Those values are 5 and 0, respectively. And from here, it's what I like to call a plug and chug, which basically means now that we've plugged everything in, we're just going to go ahead and churn through the calculations on this. Most of the time, you'll have a calculator to do calculations like this. On the AP exam, if you're taking AP Calc, usually the kinds of numbers that you're given on the non-calculator portion of the exam are going to be kinds of numbers that are a little bit easier to work with. You usually don't have to deal with decimals and roots and things like that when you get to that portion. Or when you do get to that portion, you'll see in the instructions, it'll oftentimes let you know that you can just set up a question. And if it's the non-calculator portion, they oftentimes won't make you mathematically simplify it. So just keep that in mind. But here we'll go ahead and simplify. 2 times 2.5 is 5. 5 times 0.15 is 0.75. So this will simplify to 0.75 root 3 plus 5 times dB dt equals anything times 0 is 0. We bring the 0.75 root 3 over, and we have 5 dB dt equals negative 0.75 root 3. If you divide by 5, then you're left with dB dt equals negative 0.15 times the square root of 3. If you need a more accurate decimal approximation of what that comes out to when you multiply by your calculator, then we'll have that posted on the blog with the link shown here. But for now, that's enough for us to just make sure we understand conceptually how to approach a related rates question. Now, one last thing that we want to take a quick look at on this problem. We've got a negative value here. Let's talk about what that means. So it's asking about dB dt, which means the change in the length of B over time. And if we look at this scenario, if you're pulling the top of this plank towards the roof of this building, or this line as is the case here in this example, but if you're pulling this towards the top of the page, then this piece of your figure is going to be sliding to the left. That's what we're talking about when we talk about dB dt. And as that corner of the triangle slides to the left, the length of B is getting shorter. It's decreasing, and that's what the negative sign indicates. So it's really important with these related rates questions, especially sometimes depending on the way it's worded, to make sure that we understand not just numerically what our answer represents, but also in terms of the sign positive or negative, which direction something is moving in the problem. For more, please feel free to check out our other videos, and thanks for watching.